Hello everyone. So today video we see the very beautiful function called the Thomas function. So let me write here the definition of Thomas function. So it is a function from closed interval 0, 1 to R. So it is given by f closed interval 0, 1 to R. So it is given by this way that f of x, it has a multi-part. So it is 0 if x is irrational, and 1 by q if x is rational, and the form p by q where GCD of p comma q is 1 and it taking 0 if x is 0. So this is basically the Thomas function. Now here the question we will check that so that limit extend to p fx equals to 0 for all p belongs to closed interval 0, 1. At every point we will check the limit is 0. It is clear from the definition that for the irrational part it taking 0, for the rational part it taking 1 by 2. So it is the somehow reciprocal, and n is a natural number. So if somehow if here q is a the natural number, so 1 by q sequence tends to 0. That is the intuitive idea that limit will be 0. But here we prove mathematically. So how to do? So we will use the epsilon delta definition. So let us choose epsilon greater than 0. Choose epsilon greater than 0. Okay, then by Archimedean property, there exists k belongs to n such that 0 less than 1 by k less than epsilon. This is by Archimedean property, and it is a very standard property. Okay, this property comes from the unboundedness of natural number inside R basically. Now, so we'll count how many rational number there are in 0, 1 which denominator less than k basically. So let me list it here. So the rational number 1 by 1, then I can take here denominator 1 here, this, because we are trying to list all the rational number in between 0 to 1. So now we can take here 1 by 2. Now here we can take 1 by 3 like this, and 2 by 3. Okay, we can take this way dot 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 dot, and finally we'll get here something 1 by k, and it will stop like this, and I don't know, it may be k minus 1 by k. So like this. So these are all rational number. This list is the complete list. So where the denominator of every rational number less than k. Okay, so there are because after that the rational number will be of the form 1 by k plus 1 dot 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 like this, k by k plus 1, and the same way keep going on. So from here to here are the only rational number whose denominator is less than k. This is 1, this is 2, this is 3, and this is k. So all the rational number from here to here having the denominator less than equals to k. So there are finitely many rational number. This is the main idea behind the proof of this question. There are finitely many rational numbers whose denominators is less than equals to k. Less than equal k. Okay, so in the interval 0, 1 there are only finitely many rational number which denominator less than equals to k. Okay, so now see, we have the interval 0, 1. Suppose we have the point p here. So since there are finitely many rational number which denominator less equal to k, so therefore we can find a delta such that, so there exists in this interval p minus delta to p plus delta all the rational number whose denominator will be greater than k. Okay, because there are finitely many rational number which denominator less equal to k. Suppose they are outside of this interval, we can do this. So there exists delta greater than 0 such that p minus delta and p plus delta contains all rational numbers whose denominator is greater than k. Okay, right. So it contains rational numbers whose denominator is greater than k. Right. Now we'll see the functional value fx on this interval basically. So let's check it. So basically now f of x minus 0, this absolute value is nothing but fx absolute value, and this is what 0 if x belong to p minus delta p plus delta, this open interval intersection irrational. Okay, if we take irrational point from this interval. Okay, now if x is in this interval p minus delta p plus delta, and let's say rational with x equal to, let's say, m by n, then what happened? Then this must be then n greater than k. Okay, of course I am taking GCD of m comma n equal to 1. So if you take any rational point from this interval and suppose it is of the form m by n, then n must be greater than k, because we assume that this contain the rational number which denominator greater than k. That's why it is in this form must be. So now in this case, so what we are getting? We are getting then 1 by n less than 1 by k. So basically imply then 1 by n less than epsilon. Now what happened if you take this? So f of x in this situation minus 0 mod equal to basically f of x mod. This is nothing but f of x mean m by n this mod. So this is nothing but y 1 by n. So this is less than epsilon. So what we are getting? So we get that fx minus 0 this mod equals to 0. Okay, if x belong to p minus delta p plus delta intersection q complement, and this is less than epsilon if x belong to p minus delta p plus delta and intersection q. So we get that. So we get fx minus 0 mod is less than epsilon if x belong to p minus delta to p plus delta. So we are getting that. So we are getting fx minus 0 mod is less than epsilon if x minus p mod less than delta. Since epsilon greater than 0 is arbitrary, so the limit extend to p fx equals to 0. So I think you got it. The basic idea here, the important idea is this, that there are finitely many rational points which denominator less than k. Okay, so that's why we can make a open interval around p actually such that the open interval does not contain any rational number whose denominator is less than k. So all the rational number that are lying inside p minus delta and p plus delta on this open interval, those rational number denominator of course greater than k always, right? So that idea I have used here, and which using epsilon delta definition we get the limit at every point of this function is 0. So now if you discuss about the continuity, so we finish the proof. Now it is extra part. So since the function, if you look at the function, since f of p by q equal to 1 by q, okay, which is non-zero for P by Q not equal to 0, so non-zero rational number. So which imply that F is not continuous at P by Q, because limit is 0 and at P by Q the functional value is 1 by Q. So limit is not equal to the functional value, so not continuous. But F is continuous at irrational and at 0. Okay, so this function is continuous at every irrational point, but not continuous every irrational point at 0, but not continuous at the rational point, because limit is 0 but functional value non-zero. That's why, and it is a very important function. In the Riemann integration, when you check some function is continuous, then Riemann integrable, and then you can check if it is continuous everywhere except one point, Riemann integrable, except finitely many point, Riemann integrable, and this function is Riemann integrable but discontinuous at every rational point. So countably many point the function is discontinuous but still Riemann integral. So this is an example of the function. That sense it is a good function. Okay, now see one thing in this book of this problem. Basically we have used only this logic, nothing else, that there are finitely many rational number with denominator less than k, else work are very easy, you can do by yourself. Thank you so much. So bye, good night.